So hello friends, now we are starting with magnetism and matter. मतलब इस चैप्टर में कुछ अलग ये है, इसे भी बोल देते हैं जल्दबाजी में मैग्नेटिज्म ही, और सारे स्टूडेंट्स यही समझते हैं कि ये मैग्नेटिज्म का पार्ट है. बट प्रीवियस वाज मूविंग चार्ज एंड मैग्नेटिज्म. दैट मीन्स उनमें हम चार्ज पार्टिकल के मूवमेंट के वजह से करंट कॉन्स्टिट्यूट होता था, एंड करंट के वजह से नियर बाय सराउंडिंग में मैग्नेटिक नॉर्थ एंड मैग्नेटिक साउथ फील किए जाते थे. अब हम ओरिजिनली बार मैग्नेट के बारे में ही बात करेंगे, यानी कि वी विल बी लिमिटिंग आवरसेल्फ टू मैग्नेट्स. वी वोंट एंटर इनटू करंट रिलेटेड डिस्कशन. सबसे पहले बार मैग्नेट की प्रॉपर्टीज. नंबर 1, सबसे पहले हम लोग बार मैग्नेट को देखेंगे. एंड दिस इज साउथ पोल, दिस इज नॉर्थ पोल, एंड QM पोल स्ट्रेंथ. दिस इज वाइट पार्ट इज मैग्नेटिक लेंथ 2L. मैग्नेटिक डाइपोल मोमेंट, जबकि अगर SL अरोड़ा की बात करी जाए तो ये लोग स्मॉल m से डिनोट करते हैं. एंड आगे हम लोग को पढ़ना है इंटेंसिटी ऑफ मैग्नेटाइजेशन. ये लोग कैपिटल M यूज करते हैं, जबकि वील बी यूजिंग इंटेंसिटी ऑफ मैग्नेटाइजेशन के लिए कैपिटल I वेक्टर. तो ऐसी गलतफहमी बहुत सारी होने वाली है नोटेशन के रिगार्डिंग. अब मैं क्लियर करता जाऊंगा. एंड मैग्नेटिक डाइपोल मोमेंट M इज इक्वल टू 2L into QM. दिस इज मैग्नेटिक डाइपोल मोमेंट measured in ampere meter square. दिस इज 2L is magnetic length, obviously मीटर में मेजर किया जाएगा. And QM is pole strength measured in ampere meter. So this was magnetic dipole moment of a bar magnet. तो ये तो हमने बात कर ली. Attractive property, यहाँ पे हम लोगों को ये बात करना होगा. When some iron fillings are kept, I wanted you to see the diagram. This was the diagram I talked about. अगर आप किसी बार मैग्नेट के सराउंडिंग में इस तरीके से आयरन फिलिंग्स, बहुत सारे आयरन फिलिंग्स को रख दें, तो वो आफ्टर फ्यू इंस्टेंट वो सारा अरेंज होना शुरू हो जाएगा. किस हिसाब से? एज इफ वहां पे मैग्नेटिक फील्ड लाइंस आर देयर. मतलब मैग्नेटिक फील्ड लाइंस के अलोंग ही सारे आयरन फिलिंग्स अरेंज हो जाए. जस्ट टू डिनोट दैट मैग्नेटिक इज प्रेजेंट अराउंड द बार मैग्नेट इन द फॉर्म ऑफ मैग्नेटिक फील्ड लाइंस, राइट. इसी बात को मैं नंबर 2 एट द मैग्नेटिक नियर द बार मैग्नेट. Number 3, like and unlike poles. Same way, similar to the situation of electric dipoles. जैसे वहाँ पे like charges used to repel and unlike charges attract. On the same basis, like and unlike poles या तो north या फिर south. They repel. Poles repel unlike other. 4, magnetic poles exist always in pairs. मतलब if any bar magnet is broken into 2 pieces, then like this. So this south and north will be created again. So this way they always exist in pairs, unlike electric dipoles, because isolated electric charge may remain present, but isolated magnetic poles cannot. Suppose there is one magnet is south, one all pin touched for few hours, and it is touched north pole. Here, after few hours or after few, south pole will be created, and here north pole will be created. And this process, characteristic property of magnetism, is known as magnetic induction. Then another one is directive property. What is that? For this property to understand, we need to know how Earth could be understood as a very strong and large magnet. Now I'll try to illustrate Earth as a huge bar magnet, geographic north, geographic south, but this is magnetic north, magnetic Earth as a large huge magnet. And you must be knowing, for any dipole, magnetic field lines are continuous inside the magnet poles. And what is directive property? That if any magnet is hanged, swinging magnet is hanged through a string, then in the process of swinging, after few instants, it will be aligned along the magnetic axis. So this is what I would mention in brief in terms of few keywords, that swinging magnet aligns along the magnetic axis. And there is one conceptual question, how and why. There is one conceptual question, explain repulsion, shearer test, magnetism. How and why? Suppose we are given two materials. One is, for sure, it is known that it is a magnet, like this. This we are aware of, south and north. This is also given. One more thing, and this is suspense. Whether this is, how do we get to know about this? Whether this piece of material simply a magnet or ferromagnetic. Because if it is ferromagnetic material, then either of the end we bring near to the magnet, it will be touched, it will get attracted. This will be also, and this will be also, and this will be also, and this will. In all four situations, it will be getting attracted. But if this yellow piece is a magnet, then one end will be attracted and the other end will getting repelled. Because if it is a magnet, so suppose this is north and this is, so this end if will bring over here, so it will get repelled. And then on the contrary side, if this south end will be brought near to this, then it will get attracted. So at once we'll get to know, oh acha, that means this second bar material is a magnet. Then what's the criteria because of which we could identify that this is a magnet? Not attraction, it is repulsion. Because attraction was happening in case of ferromagnetic material also. Because if it would have been ferromagnetic material, then in all four situations it would have attracted only. But in case of magnet, one end will get repelled. That's why credit is given to this repulsion. That repulsion is the shearer test of magnet. Now we can proceed towards another topic, Coulomb's law. In getting surprised how Coulomb's law has come in magnetism. Same contemporary formula. Suppose 2 point pole strings are separated by a distance r, qm1, qm2, then we are not aware of whether they are of same nature or unlike nature. Just simply 2-point pole strengths separated by distance r, then Coulomb's force, attraction or repulsion F is directly proportional to Qm1 upon r square. F is equal to, this time constant of proportionality is mu naught by 4 pi instead of 1 upon 4 pi epsilon naught. This is attractive as well as repulsive force. Magnetic force 10 raised to minus 7 Tesla meter per ampere. This is again ampere meter, meter square. है ना? Let's talk. Two magnetic poles, one of which is 4 times stronger than the other. That means QM1, one of which is 4 times stronger than the other. QM1 is 4 times. F is equal to 5 gram force. 5 gram force, that means 5 into 980 dyne. I would like to refer one conversion factor. 1 gram force is 980 dyne. 1 kg force is 9.8 Newton, and 1 Newton is 10 raised to 5 dyne. So 580 dyne, but all the data, find the strength of each pole. That is equal to, फिर strength तो ampere meter में ही आएगा. So F is equal to 5 into 980 into 10 raised to minus 5 Newton, and R is 10 centimeter. 5 into 980 into 10 raised to minus 5, 4 QM1 and QM2, right? Upon 10 by 100 minus 5 to 4 to QM2 square. Apply that 5. I'm trying to make it perfect square. 98 could be written as 49 into 2, 10 raised to minus 4. It will be 10 raised to minus 2. QM2 is equal to 7 by 2 into 10, 35 ampere meter. You must be remembering SI unit for measuring pole strength as QM2. It implies that QM1 is 4 times QM2. That means 140. Now this time two similar magnetic poles having pole strength in the ratio 1:2. Oh, QM1, QM2 is 1/2, are placed 1 meter apart. Achha. In electrostatic, we used to consider test charge all the time. On the same line, here in magnetism and matter, we keep considering unit north pole or unit pole, because equivalent of positive charge is here north pole plus 1, that means again unit pole here. So here unit pole we have all the time is smallest standard value in magnetism pole. Find the point where a unit pole experiences no net force. Suppose if we consider unit north pole whose value is 1 ampere meter, and here ratio is given. QM2 is 2 QM1. If it is north pole, let this distance be x, then this distance would be 1 minus x. But where do we require this distance? This will exert no net force. This will be force on O due to A, and this is force on O due to B. So at point O, mod of FOA should be equal to FOB. FOA means, now let's see what do we cancel. QM1, this equation. Now we'll be utilizing QM2 equals to QM1, and then 1 by x is equal to root 2 upon 414 meter from QM1. 4 pairs of forces. We won't consider the attractive force between S1 N1 and N2 S2. Rather, we'll be considering there are two magnets given, so attractive force S1 and N2, and N1 S2, two attractive force and two repulsive forces, S2 and S1 के बीच में and N1 and N2 के बीच में. So two repulsive, two attractive. फिर इन दोनों को add up करके final net attractive force and net repulsive force. Then we subtract and to get the net in this question. A steel wire of length L has a magnetic moment M. That means QM they are referring. No, magnetic moment matlab capital M. Standard relation for magnetic moment 2L into QM. Steel wire, L length, and magnetic moment. It is bent into a semicircular arc. What is the new magnetic moment? Small m is in place of 2L, now L length, L into QM. But now this L length will be bending into semicircular. Now my purpose is to find this R, pi R. Pi R is L. It implies that R is equal to L by pi. So this effective distance would be considered because separation between both the pole strengths are considered for dipole purpose. What is the new magnetic moment? Then new magnetic moment M dash is 2R into QM, and 2R is L by pi into QM, but small m is L into QM. It implies that M dash is 2 by pi L QM 2 pi into M. Properties normally. That means they come out from any surface normally also, and though these lines go into the substance normally only. Magnetic field of at an axial point, and this is also known as end-on position, and this topic is comparable to electric field due to an electric dipole at axial line. Similar topic here we have in magnetism. This is axial line, unit north pole is considered instead of test charge. Obviously this unit north pole will be getting attracted towards south pole, and again this unit north pole will be getting repelled because of this north pole. Now I'll be showing corresponding fields. This is BS, this is BN, and net, this is R, and net will be B axial. Firstly, Bs, as we used to consider kq by r square, here kqm by r square, r plus l whole square, bn qm, this time r minus l. Therefore, B axial is mod of Bn minus mod of Bs mu naught by 4 pi 2 m r upon r square minus l square whole square, B axial. And for short dipole, L square is very small as compared to r square. The axial is mu naught by 4 pi twice of m upon r cube. Like earlier we used to have twice of p upon r cube. Same way, magnetic field of a bar magnet at an equatorial point. Now equatorial line. Now here I am showing this is OP, where unit north pole is kept BS cos theta, here BN cos theta, here BS sin theta, here BN sin theta. Here mod of Bs is equal to mod of Bn is equal to B is equal to r square plus L square AQ by r square plus L square whole square. I'm not going to do full derivation. Instead, I'm just writing important steps and then final relation. So this is B. Therefore, for net field B equatorial is Bn cos theta 2 Bs mu naught by 4 pi um by, and lastly cos theta is based upon hypotenuse, that is equal to mu naught by 4 pi 2 qml is capital M magnetic dipole moment, vectorially mu naught by 4 pi. This is similar expression as we used to get in electrostatics. Then for short dipole m upon r cube. हमने lastly broadside on position और equatorial line due to dipole पढ़ा था. See, this was our heading, last heading, due to a bar magnet at an equatorial point or broadside on position. Here we found this was the expression. Then for short dipole minus m upon r cube. Then thereafter एक और चीज हम लोग कर सकते हैं, वो ये है रेशियो ऑफ एक्सियल फील्ड एंड इक्वेटोरियल फील्ड एट अ पॉइंट डिस्टेंस r due to short bar magnet mu naught by 4 pi twice of m upon r cube. Here mu naught by 4 pi m upon r cube. Therefore 2 upon 1 is equal to 2 is to 1. South qm north, and this is magnetic dipole moment. So here also I may write theta qmb, pair of equal and unlike forces having different lines of action constitute magnetic torque. टॉर्क वाले सारे सिचुएशन में नेट फोर्स 0 होते हैं. Then torque tau is either force into perpendicular distance between parallel forces. फिर either force that is QMB into perpendicular distance between parallel forces. This is 2L cos theta, 2L sine theta. That means this distance, perpendicular distance between this is perpendicular distance between the equal and unlike forces. That was 2L sine theta. That is equal to 2UML. B sine theta is equal to MB sine theta. Tau max is MB when theta equals 90 degree. One more point of discussion, direction of torque. Like electrostatics, we already had direction of magnetic torque, tau. First vector M to second vector B clockwise. Therefore, downwardly perpendicular to the plane of M and B. So this way it was direction of the torque, tau, meaning stable equilibrium, that is that theta is equal to 0 degree, tau minimum is equal to 0, and again at unstable equilibrium, tau 180. Now this is also done. Now any more point? Defining magnetic dipole moment on the basis of torque. Think B is equal to 1 Tesla and theta is equal to 90 degree, so that sine theta is also 1. Hence M is defined as the torque acting on a dipole held perpendicular to the uniform horizontal field of unit strength.